Good morning. We're going to discuss today regarding the QAM. So I told you in the last class regarding this QAM, what is an idea that is used to generate a say quadrature amplitude modulated signal. QAM means quadrature amplitude modulated signal. Okay, what idea is used here to generate this QAM signals that we need to discuss. Okay, so for that what I need is, first I need some background to know how exactly this amplitude will going to be represented in the form of vector. Okay, so this discussion is all about QAM. Yes, so basically it is a combination of two things. One is PSK, another is ASK. Now why we had gone for this type of a hybrid thing? The idea used here is the basically to increase number of bits per signal element. Okay, now what is the problem with the PSK? I will tell you. When I talk about going for a multiple say phases, if I say in PSK is best among ASK and FSK, that is at least concluded. Now if I plan to use only PSK by increasing number of say phase levels, then it makes the system more complicated. Anyway, if you are talking of increasing say going for a more say phases, it will go to have some limitations. So you will not be allowed to increase beyond some level. Okay, so at most you can increase it to 8 different say phases. Okay, beyond that again it makes the things more complicated for the receiver to understand. Okay, but anyway, by clubbing this with the ASK, it gives me a lot of say options for increasing the signal element. Now see, my signal element in this case is two things. These two together will going to act as a signal element now. Okay, so this allows me, or this gives me a say tool for increasing more number of signal elements, because I have two options now, two characteristics of the signal I am dealing with. One is amplitude, another is phase. Okay, now to understand this, okay, if I go for say your amplitude time graph, it is difficult to draw these things. Okay, because I have to change amplitude, I have to change the phase of a signal. So to understand that, I will rely on say something similar to your vector diagrams what you have studied in your PUCs and all. Okay, so we call here it as a constellation diagrams. So we use these constellation diagrams to understand how exactly these QAM signals will going to be represented. Okay, I will use this tool. Okay, so this will help me to say represent the different signal elements, which is combination of phase and amplitude. Okay, now how exactly it will be? So to start with, I will talk of representation of the amplitude as a vector quantity. Okay, so when I talk of vector quantity, I need two components. For representation vector, we're going to have both say magnitude as well as direction. Okay, now the component one which is along the x-axis. Okay, so I'm going to call it as I component. I think you might have come across this type of representation while you are studying in a first year. Okay, so when it comes to a basic electrical subject, this type of representations was used when it comes to representation of impedance. Okay, then Q component along y-axis. So Q here indicates quadrature. So I indicates in phase. Okay, so quadrature and in phase. Say Q component. Okay, now if your signal, okay, now here I am talking regarding representation of amplitude with help of this type of say diagrams. Fine. Now if your amplitude is not making say any phase angle with say reference. Okay, if its phase is 0, if you have a signal whose phase is 0, it starts with 0 phase, in that case this particular signal will going to be lying on y-axis, x-axis, depending on this length will going to be depending on its amplitude. Okay, amplitude will decide its length, and phase, since it is 0, it has to be on y-axis, I mean x-axis. Now if phase is having anything other than 0, say something 45 degrees, in that case your this amplitude will going to make some angle with this reference. Okay, so this is the amplitude, this length is representing the amplitude, and this angle which is making with this say x-axis will going to represent your phase. It is going to represent your phase. This angle will going to represent the phase. Okay, so this type of a diagrams helps me to understand how QAM will be useful and how exactly the number of signal elements will be say increased when it comes to a QAM technique. Okay, now to start with, I will talk regarding representation of say ASK using this constellation diagrams. Okay, now ASK, you see I am talking regarding in ASK amplitude shift keying, two amplitudes. Okay, one is say some V volts plus V volts, other amplitude say for understanding reason I will take it as 0. Okay, for understanding reason I will take it as 0. So if I talk of representation of this in the form of constellation diagram, now see this is a positive voltage and this is a 0 voltage. So what about the phase? Phase angle is not mentioned. It is by default it is 0 because I am not bothered regarding the phase. We are not varying the phase here. So in this case, the representation of these two voltages will be lying on x-axis. One is with 0 amplitude, another is with plus V amplitude. Okay, so this will be along x-axis itself. Okay, so this is my say plus V is equal to 5. So in that case, this length will go to be representing 5 volts. This length will go to represent the 5 volts. So this is 0, this is 5. So this is the way ASK will go to be represented. In case if I use something other than this, say plus 5 volts and say plus 2 volts, in that case you see your ASK will going to be somewhere over here. This is one which is representing plus 2 volts, whereas this is representing a 5 volts. Now see, this is what is the magnitude from reference, okay, which is indicating 2, which is representing one, say ASK amplitude, and another is 5. So if I try to represent this in the form of say amplitude time graph, it will going to look like this. I have a two signals, I have a signal with two different amplitudes. Okay, so this is your 2 volt amplitude signal and this is your 5 volt amplitude signal. I'm here talking regarding peak to peak. Okay, plus 5, that's the reason I said. Now, for understanding reason, I am talking of these values. Now, this value, okay, this is this value, this is one signal element, this is another signal element. Now, what happens here? In the end, I have a two signal elements which are going to be represented in this way. Now, I will talk regarding QAM. Okay, sorry, FSK. Okay, when we talk regarding a FSK, okay, so in say rather than talking about the FSK, I will talk about the PSK. So FSK, it is difficult for me to represent here on this constellation diagram because the frequency is getting changed. So when it comes to a PSK representation, okay, so I'll assume that, say that what we have discussed a PSK as an example, in which I have a signal with 0 phase and I have a signal with 180 degrees out of phase. There are two signals which are changing in phase, but their amplitude will go to remain constant. It will be V. So with this assumption, I will represent now. So now see, one is making an angle 180 degrees, another is making an angle, say your 0. So 0 component, the one which is making a 0 will going to be represented here, which is plus V. So with amplitude will remain same. Amplitude will going to remain same, that is V. Okay. So this component is in phase. When it comes to another bit which is going to be represented with a 180 degree phase, see, this is 180 degrees, it will going to be represented here. So this will be the second signal. This will be the second bit. So this will going to represent a 0, this will going to represent a 1. So 0 and 1 will going to be represented on x-axis itself. So here it is making a phase angle 0, here it is making a phase angle 180 degrees. Okay, so this way we talk of representation of PSK on this constellation diagram. Okay, now when I talk about the QPSK, just recall that what we have discussed in the last class, quadrature PSK. So where I used four different phases, say 45, minus 45, 135 and minus 135. So this I need to represent over here, and for all these four cases the amplitude will go to remain constant. Yes, so that means I am going to have four dots like this which are representing the amplitudes with different phase angle. This is a 35, this is 135. Yes, so like this you have 4 points which are represented on 4 different quadrants. This is your QPSK. Yes, this representation is for QPSK. Fine. So when it comes to see, now these are my 4 signal element. Now look at the way in which I am representing, which is very simple, easy to understand now. Say I can call it as 1 1 0 1 1 0 1 1 like this. Okay, I can use the notations. Say anyway, it is left to you what kind of a values you want to assign to it. So there is no 0 0, so it has to be like this. This I am going to call it as 1 0. Okay, so this representation is representing a 4 signal element. This is one phase component, this is the second phase component, this is the third one, this is the fourth one. Like this, I have four different phase components. Okay, four different phase components which are representing my bits. So these are my four signal elements. Yes. Now I will talk regarding QAM, quadrature amplitude modulation technique, where I will going to combine, say, this ASK with PSK. I will going to combine ASK with PSK. How exactly it will going to work out? Okay, so I will going to show you some different figures where the phase angles will going to be of a different types. Okay, so here two things will going to represent the signal element, one amplitude and phase. Okay, now I have one component with amplitude 0, yes, and phase 0. I have another component with amplitude some value and phase angle 0. I have a third component, okay, whose amplitude is, say, some value same as this, plus V, okay, and its phase angle is 90 degrees. Yes, its phase angle is 90 degrees. And I have one more component whose phase angle is 45 degrees and amplitude remains same. So like this, I have a four component. Now see, this is representing a signal whose amplitude is, say, some V, amplitude is V, and phase angle is 0. This point is representing amplitude 0, phase angle is 0. Now see, V is amplitude and phase angle is 0. Amplitude is 0, phase angle is 0. Here the amplitude is, say, some V and phase angle is 45 degrees. Here the amplitude is V, phase angle is, say, 90 degrees. Yes. So like this, I have a four components with different phase angles and different amplitude values. Okay, I have a four components which are, say, of different phase angle and different amplitude values. So this leads to this kind of a representation. So now see, I had more option here. So with the help of only two phases, I mean three phases, okay, I am talking of representing, say, four signal element, and this type of a representation will go to lead to a very simple representation. Now see, actually when you talk about this and this component, their representation will go to be very easy. Only the problem is with my 45. Okay, same thing if I say expand. Okay, so this we call it as 4 QAM, 4 quadrature amplitude modulation scheme, 4 QAM. Okay, now like this I can go for 16 QAM. Like this I can go for a 16 QAM. So where I can use four different phases, four different amplitudes. So together it will go to give me a, say, here what happened, two phases and two amplitudes, altogether it is giving me a four options. In next case, you see 16 QAM, I'll talk of representing the components like this in four different components, four different quadrants. Okay, so like this I have a 16 signal elements which is combination of, say, your amplitude and PSK. So this gives me a representation of 4 bits per level. 4 bits per level, because 16 signal elements, 4 bits. Just imagine, so your R will go to be increased. Okay, your R will go to be increased by, say, very large value. So this in turn helps you to reduce the bandwidth and data rate will go to increase. So this type of a representation which is widely used in a mobile communication to improve the data rate. Now see this representation where I am talking of representing 4 bits per signal level. So this is representing 4 bits, this is representing 4, this is 4 and this is 4. Like this I can have a 4-bit representation for every signal element. Okay, so like this 16, you can go for a 32 and so on. Okay, by changing amplitude as well as phase, you can go for a more levels. So by this you can increase the bit rate, which is normally the technique that is preferred in different, say, generation of say mobile communication and all, where they can increase the data rate by this way, by these type of a representation. Okay, so this is regarding QAM. Okay, so this completes this particular chapter, which is connected with digital to analog conversion. Okay, all three basic schemes plus QAM we have discussed. So I hope so these things are clear, and we'll discuss one simple example. Okay, few examples we're going to discuss which are based on say this digital to analog conversion. In the last class we have discussed. Okay, now we'll see some different kind of examples, and say I will try to utilize this particular time so that we will try to attempt more examples which will be useful for you from the point of view of your examinations. Okay, so say still some time is there, I can think of say attempting few examples. Okay, so I'll first read out the problem. Okay, we need to send 3 bits at a time at a bit rate of 3 Mbps. The carrier frequency is 10 megahertz. Calculate the number of levels. See, here the thing asked is, say they want to send 3 bits per signal element. Yes, 3 bits at a time. That means we are talking of sending 3 bits per signal element, and bit rate is 3 Mbps. Bit rate is 3 Mbps. I hope it is clear. So the carrier frequency is 10 megahertz. The carrier given is 10 megahertz. Okay. Calculate the number of levels. Calculate the number of levels, baud rate and bandwidth. 3 things he has asked. Bit rate is given, baud rate and bandwidth along with number of levels. These are the 3 things which is asked in the problem: baud rate, bandwidth and number of levels. Okay, to start with, I'll start with the number of levels. Okay, now you know that number of bits given is 3. So as you know that say that number of bits per level. Okay, bits per level, just recall that bits per level which is given by log 2 to the base n. Okay, but here number of bits per level is mentioned, that is 3, and he is asking this quantity L. So L is equal to 2 raised to 3, so it is 8. Number of levels is 8. So I am talking of taking a say inverse of this log, so NT log, so which will going to give me a 8 levels. Okay, so this is regarding bits per level. So the bits per level is 8. Next is say he is asking regarding baud rate. Okay, so how many bits you are representing per level? 3 bits. So bit rate given is 3 megabits per second. So your baud rate S will going to be given by which formula? So that is N into 1 upon R. Okay, so R value will going to become 3. If R is 3, this is 3 Mbps into 1 upon 3, which will lead to the answer say which is equal to 1 megabaud. This is Mbps. I'll keep it in Mbps only, so rather than converting it to say bits per second and all. So better keep it that way. So 3 gets cancelled. Very simple example. So that means my answer will going to be 1 megabaud. Signal rate is 1 megabaud. So now last part is the bandwidth. Okay, so last part is the bandwidth. Now say again The carrier frequency given is 10 megahertz. Okay, and if I assume that it is FSK, I'll try to solve it in connection with the FSK to find out the bandwidth. Okay, so here one assumption I will do. Okay, so that my 2 delta f is 1 megahertz. Okay, so if I take it as 1 megahertz, okay, if carrier frequency is 1 megahertz, that okay, then 2 delta f will going to become, so you see, simply you keep it this way, you take it as 2 delta f is equal to 1 megahertz. This quantity I have not mentioned while writing the given values. Okay, so you take it you take this 2 delta f as 1 megahertz. Okay, now I will go to calculate the bandwidth. Okay, so bandwidth B is equal to 8. 8 is because that number of levels, 8 into say 1, it equal to 8 megahertz. Okay, bandwidth is 8 megahertz. So this is regarding this example. So all 3 things has been obtained. Now I will talk regarding the one more example. We'll see to it. Wait, I'll just check it out. So this is not connected with this analog and digital to analog conversion, but say this particular example is again also based on that same formula, S is equal to N into 1 upon R into C. Okay, so now I am trying to attempt the examples which we have not yet discussed. Okay, yesterday I was say going through one question paper in which this particular question was asked, which is related to the second module only, and in one of the classes we have already discussed regarding this. Okay, so I am going to discuss that particular example over here. So in digital transmission, receiver clock is 0.1% faster than the sender's clock. Receiver's clock, see, it is connected with synchronization. So receiver's clock is 0.1% faster, 0.1% faster than the sender's clock. See, the receiver's clock is fast here compared to that of the sender. Okay, so this is the clock value, how much it is expressed in percentage, how much fast it is in comparison with the sender's clock. So receiver's clock, if it is 0.1% faster than the sender's clock, how many extra bits per second does the receiver receive if the data rate is 1 kbps? If the data rate is 1 kbps, how many extra bits it will going to receive? This is what is the question asked. Basically, it is a kind of a synchronization technique. Say, now say 0.1% of 1 kbps is how much? It is 1. 0.1% of 1 kbps is 1. So if it is 1, the number of bits, extra bits, what it will going to receiver will go to receive is 1 extra bit. So anyway it is receiving 1000 bits. Along with that 1 extra bit, that it becomes 1001 bits. How many extra bits? It is going to receive only 1 extra bit. So total bits what it will go to receive is 1001. This is the total bits what receiver gets. Yes, so it is 1001. Okay, so actually this is an error, just to indicate that if there is a mismatch in the clock values, so actually the receiver has to read this as 1 kbps only, but the problem is the receiver's clock is faster. Okay, so because of that fast nature of the receiver's clock, it will going to receive some extra bits. That extra bit, say extra bit is creation of the receiver. Extra bit is creation of the receiver. So actually it should receive 1000 bits only, but due to this error it is treating that 1 kbps as 1001 bits. It is treating that 1 kilobits which are transmitted in 1 seconds. Okay, it will treat it as 1001 bits in 1 seconds. Okay, this is an error. That is because of this change in the clock. Okay, so this is related to the synchronization. Okay, one more example is there. Let me check it. Okay, this is last example which I am going to discuss today. A signal is carrying a data which is one element. Signal is carrying a data in which one data element is encoded as one signal element. If the bit rate is 100 kbps, what is the average value of baud rate if C is between 0 and 1? See, the quantity is given here is that C which is between 0 and 1. So I'll assume, see here you have an option of assuming, say because 0 and 1, the value of C is between 0 and 1. C is a case factor, you are already aware. So normally what we do is we take case factor is equal to 2. Since it is between 0 and 1, the between values or a mid value of these two values is half. So I'll take it as say half. And next what is said is say number of signal elements and data element, that ratio is given. Okay, so one data element is encoded as one signal element. One data element is encoded as one signal element. Fine. So this means it will going to give me a ratio of these two values which is indicating R. So my R value is 1. So two quantities I have obtained. Say then if the bit rate is 100 kbps, he is talking regarding bit rate. Yes, bit rate is 100 kbps. So this is nothing but your N. This is nothing but your N. Okay. What is the baud rate? What is the baud rate if C is between these values? Okay. So I'll use that formula. The same formula that what we have discussed previously. So when it comes to a digital to analog conversion, the same formula which I used, where the C case factor I have not taken it. Normally we used to assume it as 1. Okay, so this is C. So here N was 100 kbps. My R is 1, so I'll just ignore it, and this becomes 1 upon 2. Case factor is 1 upon 2. So this equal to 50 kilobauds. This equal to 50 kilobaud. I hope it is clear to you people. And today I'll end the stream over here. If you had any doubts, you are free to ask me through WhatsApp. Okay, or otherwise you feel free to call me. I don't have any issue. So in the next class I will going to start discussing regarding multiplexing. So that is a new topic. So rather than say start discussing regarding that multiplexing now, okay, I'll say keep a time. So I start it from Monday. I'll start it from Monday. So if you had any doubts, you are free to ask it through WhatsApp. Okay, so now I'm going to end the stream. Before ending the stream, please enter your USN in a comment section.